Okay, so today I am going to discuss another problem from CSIR NET June 2023, and this year actually I wrote this exam. So this is a topic from electromagnetic induction. So this is actually a good concept. Now let's read the problem and pause the video first and give a try by yourself and then look at the solution. Okay. So the statement is an infinitely long solenoid of radius r naught centered at origin which produces a time-dependent magnetic field of this amount. Okay, and is placed along z-axis. It is placed along z-axis, and a circular loop of radius r which carries a unit line charge density is placed initially at rest on the xy plane with its center on the z-axis, and it is given that r capital R is greater than r naught. So the magnitude of the angular momentum of the loop, okay, the loop of radius r, okay. So this what is the angular momentum of this loop, okay. So let me first summarize and try to draw the diagram for you that what are given. So it is a z-axis, okay, and here is a infinite solenoid. Okay, it is up to infinity. Okay, so this is a solenoid, infinite solenoid, and this solenoid has some radius, and there is a magnetic field, time-dependent magnetic field, that is alpha by pi r0 square into cos omega t. Okay, and there is another loop that is capital R of radius capital R, and this capital R is greater than R naught. So this is the situation, okay. And this radius, this capital R loop carries a plus one, that is unit line charge density. So lambda is plus one. So you have to calculate what is the angular momentum induced in this loop, okay. So what is the angular momentum? Okay, so you may get it or may not get it, but we mainly have to use the third Maxwell's law, that is del cross E is equal to minus del B del T. Okay, so if a magnetic field is changing inside some area, then the electric field is induced across that area. Okay, so this is the third Maxwell's law, and this is the formula which we will going to use for this problem. Okay, so first look at the statement of the question, that magnetic field is valid only for the region R is equal to R naught. So greater than, for R greater than R naught, there is no B. B is equal to 0. Okay, so your flux is only inside this region 0 less than R less than R naught. Okay. So what to this is the flux inside the radius R also. If R greater than is R naught and the magnetic field is valid only for 0 less than R less than R naught, then the flux passing through the radius R naught is also the flux passing through the radius capital R, right? Because R naught is less than R. Okay. So the flux passing through radius R or radius R naught, that is alpha by pi r0 square b dot ds cos omega t, and the area in which this magnetic field exists is this. So simply cancel this. So it is alpha cos omega t. Okay. So this is the flux passing through radius r naught. Okay. But as capital R is greater than R naught, so this is the also the amount of flux passing through the circular radius R. Okay, so this is the circular radius capital R, and there is a small region small r naught, and inside this region there is the flux phi. So this is the also the flux inside this capital R. Okay, so this is the flux. Okay, now del cross E is minus del B del T. So you can just simply do a del B del T ds and del cross E dot ds in both sides, and by Stokes theorem it will change. So it is E dot dl is equal to minus del T of the flux, right? So this is the amount. This is the another form of third Maxwell's law. So if this is also the third Maxwell's law. Okay. So the electric field across this loop of radius capital R is E into 2 pi R is equal to minus del T of the flux is alpha what is the value alpha cos omega t right, alpha cos omega t. So if you differentiate cos, it will minus sine, and there is a omega also came outside because of this differentiation. Sine omega t. So E is 2 pi r. And what is the direction of this E? E is direction is phi at. So E is just in circular direction. So suppose this is the directions. This is the directions of E. Okay, so E goes along this. Now assume a small. Now suppose this is the circular loop, and suppose this is a small element. Suppose this is the small element of dq, and the force on this dq is E into dq. Okay, now assume this region. Now E is fixed. Okay, E is, sorry, it is 2 pi r. So in this expression of E, only the time is varying, but space is not varying, it is fixed. So the value of E is fixed at every point in this loop. So the value of force in every dq will be dq, e dq, e dq, right? So this is e dq, e dq, e dq, e dq, e dq. So this is fixed also. Okay, so your force, suppose a small amount of force in a small area, small region, that is lambda e into dq, that is lambda r into d theta, right? So this is suppose a small area, lambda r into d theta. Okay, so this is the small dq, and lambda is equal to plus 1 given. Okay, so E into r into d theta, this is the amount of small amount of force. Okay, so what is your small d tau torque? Okay, so suppose there is a rim and you are applying some force F in the rim. So what is the magnitude of torque? Torque is simply r cross F, and r F are perpendicular. F is tangential, r is radial, so they are perpendicular, so they are simply r into F sine 90. Okay, so d tau is simply E into r d theta into r, so E r squared d theta. Okay, now if you integrate it over the whole d theta, it will give you a simply a 2 pi. So 2 pi E r square, right? Now this is your expression of E, and multiply it your 2 pi r square. So it will be alpha omega r sine omega t. This is your tau. So you get the expression of tau, that is torque on the loop. So now your torque is simply the rate of change of angular momentum, right? So dl dt is simply your alpha omega r sine of omega t. Okay, so now you can simply integrate it on both sides. Suppose your initial angular momentum is 0 and final angular momentum is L, and your initial time is 0 and final time is t. Okay, so you will get L is equal to alpha r. You will the omega will be cancelled because of this integration. Okay, so your it will be 1 minus cos omega t. Okay, but suppose you don't do this definite integration like 0 to 0 to t, then you will simply get alpha omega r cos omega t plus some constant, plus some undetermined constant, let's say. So suppose you get this is it as your answer. Okay, now suppose you can check the options. So this option will surely not come, this option will surely not come, this cos 2 omega 2 has no possibility. So these three options are has no possibility to come. So only the valid option will be this with some positive constant. Suppose you arrive at this option with some constant c1, indefinite integration, indefinite integration because of this indefinite integration, but there is no chance of coming these options. Okay, so this will be the most suitable option. Okay, if you don't do the definite integral at all. Okay, so this is a good problem from electromagnetic induction, and there are many problems like suppose I am giving you a sample problem, like there is suppose let's just suppose there is a disk. I am giving you the problem by my mind, and you may solve it. Okay, this is a good exercise maybe. So there is, suppose, a disk of mass m and radius r, and it is moving in some cross magnetic field. There is all that cross magnetic field. Okay, suppose there is cross magnetic field of magnetic field amount b, and suppose uh, it has some charge density, say sigma. Okay, charge density is sigma. Okay, and there is it is moving on a rough surface. It is moving on a rough surface, and it is moving on the rough surface such that it is not slipping. No slipping, pure rolling. Okay, so you are given that no slipping, pure rolling. Okay, so you can use this condition, and now you have to suppose what you have to calculate. Let's say what is the value of frictional force acting on it. Okay, so you can calculate it. So you have to mainly calculate that what is the amount of force acting on it, and you have to write the equation of motions, and torque is equal to I alpha. Okay, so basically you have to write these two equations. You can do this, or you can simplify this. Don't think as a disk. Suppose you can first solve it as a ring. It is a ring of mass m and radius r, because then you have to do integration to find the, if you think it is a disk, then sigma is distributed uniformly on it. Then you have to do integration to calculate the torque, because every point had some radial distance r, and you have to integrate, do a special integration also. But if you think it as a ring, then r is fixed. Okay, so you don't need to do integrations. Okay, so first try it as a ring, and then try to do it as a disk. Okay, so this will be a good problem from punch of rotation, and this concept that induced magnet electric field concept. Okay, so this will be a good problem also, and you can also calculate the value of I if resistance R is given. Okay, so this kind of problems may come in this exam. Okay, so this is a good concept from electromagnetic induction. Okay, so that's it for today, guys, and thank you.